So today we're going to talk about error detection and correction, large-scale conversational systems. Before we dive into it, maybe we can start with introductions. I'm Amal Iyer. I'm a staff data scientist here at Fiddler, working on explainability and model monitoring. I would love for our listeners to get to know a little bit about your background, Pradeep.
Hi, everyone. I'm Pradeep Natarajan, a principal applied scientist at Amazon's XAI division. My background is largely in computer vision and machine learning. I have been doing this for nearly 20 years now, going all the way back to my undergraduate summer internship. And at Alexa, I have been working on various initiatives, including adding multisensory capabilities to Alexa, as well as error detection and correction at the scale at which Alexa operates. And that would be the focus of our talk today.
Right. Yeah, it's super impressive, the track record you've had in ML and contributed to Alexa's sort of story the past several years. So maybe let's dive right into it. I'm very curious about how did Amazon get to building Alexa and the story behind it?
Yeah, absolutely. And as we go through this talk, I'll also be using the slide deck with me to sort of convey some of the key ideas and concepts. So in terms of Alexa's origin itself, it is in some ways very much what you would expect. It was inspired by science fiction. As you would imagine, there are a lot of Star Trek fans across the tech industry, including at Amazon. And a team of scientists and engineers set out to build a computer in the cloud inspired by the vision in Star Trek that could be completely controlled by your voice. And right from early on, they had the vision of a voice experience that could be built into everything and be available everywhere, right? So that's the origin story for Alexa. And like everything we do at Amazon, this also started from a working backwards document, right? We have a strong set of leadership principles that many of you who might be familiar with Amazon are aware of. We are obsessed with the customer. This is something you can see in every service that from Amazon that you interact with, right? Whether it is your retail package deliveries or your interactions with AWS, or with your Alexa devices at home, we are constantly obsessed with what the customer wants and how we can address them, right? So that is a core tenet in our processes. And we worked backwards from a set of actual use cases that customers would be interested in using a voice assistant for. So those were the two key components. We drew inspiration from science fiction, but also grounded it in actual customer use cases that is consistent with Amazon's leadership principles overall. So that's sort of the origin story, Amal.
Yeah, it's pretty impressive because one of those defining moments in tech in the past decade. Now, I'm pretty sure, like me, a lot of listeners are interested in getting to know the signal processing chain, or what happens behind the curtain the first time they call out Alexa. Would love to know a little bit more about that architecture.
Yeah, absolutely. So there are four key machine learning tasks that Alexa had to be good at to get it off the ground, right? The first is wake word detection. When you say Alexa or Amazon to your device, we have an on-device model running to detect that and then start processing what you say after that, right? So once we start listening to what you say after that, we needed an automatic speech recognition system that takes the audio and then converts it into a text, right? If you say, play music by Michael Jackson or something like that,
right,
that audio stream, we first need to convert it into text. And then the third piece is the natural language understanding, right? How do you understand what the user is asking for? Is the user asking to play a song, or is the user asking for general information, so on and so forth? and what are the entities mentioned. If you say play music by Michael Jackson, that's a different entity from play music by Elton John or something like that. And then the final piece is, once we have processed your utterance and come up with a response, we need to render it back to you in voice again. So there is a text to speech system as well. And then we wanted to also expose all of this technology to developers so that they can build their own experiences and skills that build off of these underlying core technology. So those are the key components. And just to give you a little bit more detail into what happens in these models, right? If you look at the wake word model, this is a illustration from a recent paper in interspeech by scientists at Amazon. We have.
I'm sorry, I'm just going to interrupt you there. Are you sharing a slide as well? I can see the first slide. Are you?
I am sharing the slide, but can folks see it or not?
At least I'm only able to see the.
Can you see
now?
it now?
I can see it now. Perfect.
Okay. I think when I do full screen, it's probably not showing it. So
Okay.
let's go with this. Hopefully, it's visible to folks.
Yeah, it is.
Yeah. So in terms of wake word detection, we look at the audio stream and we apply a convolutional neural net based model to on a sliding window, right? To detect if the wake word has been uttered, right? And we have been continuously improving this model over time. And this particular illustration is from an architecture that we published just this year at interspeech. Then in terms of automatic speech recognition, once the wake word is uttered and then we open the mic to listen to what the user is saying after that, we have a recurrent neural net based model that processes the utterance and converts it to text, essentially, right? It has it jointly recognizes the language. It also uses contextual information as well as acoustic features, and then produces the utterance transcript. And once you get the utterance transcript, the natural language system comes into play, which first classifies the utterance into one of multiple domains that we have, right? Music or movies or books or such. And then that system also tags the entities mentioned in the utterance, like Michael Jackson or album names and such. And then we take those entities and search our entity databases to get to get a set of answer candidates. And then we have a ranking module that ranks the different answer candidates that we have produced. And then finally we select the top one, right? So this is all happening in the natural language understanding system.
Right.
And then finally, we have a neural text-to-speech model that is converting the response we have created through our processing back to the user to get a voice-based response to the user question.
Gotcha. So it seems like it's a cascade of really complex systems, but also they're modular in nature. It's fascinating what that single keyword triggers in the back end, and how all of this comes to life to deliver a great customer experience. Speaking of experience, can you talk about the journey that Alexa has had since inception and where you are now compared to the launch?
Absolutely. So again, I mentioned Amazon as a company and culture is obsessed with the customer, right? We made a customer promise when we launched Alexa that we will continuously improve and make Alexa smarter and more useful to our customers, right? So to quantify the journey that we have done to improve the customer experience, if you go back to 2014, what did we launch, right? We launched Alexa on one device, right? The original Echo device. And there was one developer, which is Amazon itself, and one language in which we launched. And we had a total of 13 skills available on Alexa. Now, fast forward to today, where are we now, right? There are 140,000 plus devices which now have Alexa embedded in them. There are 15 language variants that we support today, more than 100,000 developers in our 3P ecosystem who have built, more than 100,000 skills that are all available to you, right? So, so if you sort of can visualize the competency graph, since 2014, we have grown exponentially in terms of the skills and capabilities we are able to support. And our error rates have come down while we have been scaling up along these lines, right? So just to give you some sense of the relative improvements we have achieved, the wake word and speech recognition systems error rates have come down by a factor of 4. The natural language understanding system, the error rates have come down by a factor of 3, while we have expanded the range of utterances we are processing, right? And then finally, if you look at our text-to-speech system, we have bridged more than 80% of the naturalness gap between what Alexa is, how Alexa sounds, and how a natural human speaker might sound, based on some
Mm,
third-party studies that have measured this.
right.
So that's sort of the magnitude of progress we have made in the past several years.
It's incredible. And I think it's borne out in customer experience and how Alexa has sort of, made its way into myriad devices. It definitely seems like you had to balance not just scale, but also complexity. Could you talk about the technical challenges that you've had to encounter and surpass in this journey so far?
Yeah, absolutely, right. So in terms of some key sources of error in a complex machine learning system like this, is that first of all, Alexa is not one model, right? There are multiple models that are processing utterances in a sequence, as well as models that are simultaneously operating and such, right? And a failure can occur in each stage of the pipeline, right?
Mhm.
And also, the error patterns that we see are often related to specific design and modeling choices that we need to make to support the scale and diversity of utterances we are handling. And the final thing is, one of the flip sides to all the progress we have achieved is that the errors we are seeing in the system are relatively rare and difficult to identify, right? So those are all some of the key challenges we face in order to continue improving Alexa and delighting our customers.
Right. Yeah, definitely. It's. I think when we were talking before the session, you had mentioned how it's a needle in a haystack problem that you're trying to solve. Maybe you can sort of talk
Mhm.
about the ways in which you are addressing the sources of errors.
Yeah. So first, I will, describe. I'll again re-emphasize the high-level mindset we bring, and also dive deeper into one specific error detection system that we have built, right? Um, so, the one of the things is that um, um, we are continuously improving our core models, right? And then we also have a relentless focus on identifying and correcting errors. And then finally, we are developing breakthrough AI technology that enables self-learning, natural, and conversational interactions, right? Um, in terms of detecting and correcting NLU errors, um, um, uh, uh, there is one particular system I want to dive a bit deeper into.
Mhm.
So just to introduce the problem that we are tackling, if you look at a large-scale conversational assistant, we are processing billions of utterances every week, and these are typically partitioned into domains such as music, movies, weather, wiki, and such. And customer experience and model artifacts for each of these domains are managed by independent teams, right? And how does this modularized NLU system look? So what we have is, if you have utterances belonging to the books domain and music domain and so on and so forth, each of these are separated. So we have separate domain classification, intent classification, and named entity recognition models that are managed by each of these domain teams. And they build their own one versus all classifiers for each of these models, right? And this is a well understood pattern in large scale conversational assistance, which allows us to scale, right? So if you visualize the hypothesis from individual domain models, say you look at the books domain, we have a domain classification model that is saying the probability of membership is 0.6, right? And these are all illustrative numbers.
Right.
And then we have various intents like read book intent or find book intent, and each of them have a different confidence. And then we have a named entity recognition model that is tagging the named entities and classifying, right? And then you can aggregate all of these hypotheses from each individual domain models, and then look across the different domains as well. So that's the broad system, right? And why is this architecture useful, right? As I mentioned, it allows rapid scaling to support multiple domains, catering to billions of diverse utterances. The domain teams operate independently and update their models asynchronously. It eliminates cross-team dependencies and enables rapid deployment of fixes and new features, right? But this scalable architecture also creates a unique problem, which is the domain false route problem, right? And what exactly is this problem? It is that an utterance belonging to domain X is instead mistakenly routed to a different domain Y, right? Why are these hard to detect, right? Let us consider an illustration, right? Again, these are all illustrative numbers, not really representative of anything there. So if a domain X is, say, 0.5% of the total traffic, and we are misrouting 20% of these utterances, that means the actual error utterances we are looking to find is 0.1% of the overall traffic, right? So this is the classic needle in the haystack I was talking about.
Right.
And how can we detect these false routes? Right, manually sifting through these billions of utterances and identifying these false routes is infeasible. So we need a model-based approach to scale, but models need data. And in this particular problem, we need a model to find the data in the first place. So we have a circular dependency, and this is where we used transformer models, right? So some of this content might be sort of quite familiar to a lot of the audience here. Transformer models, to simplify, you're given an utterance, they apply a series of nonlinear transformations to convert the utterance into an array of numbers, right? And then you can take those array of numbers and feed it to a downstream classifier, right? That's what transformer models do. But one unique thing is that they can be pre-trained on a data-rich task and then fine-tuned for a task with limited data, like our false route problems, right? So that's basically what we did to detect utterances, right? And details of this is actually published in ACL this year. So what we did is we took an utterance and embedded it with the Roberta model, and also took the hypothesis from our production system and concatenated embeddings of these, and then fed the concatenated feature vector to a downstream feed forward layer. And then we trained this whole system end to end. We fine-tuned the whole system end to end with a small training data set of false reject utterances we had to train our false reject detection model, right?
Gotcha.
And this sort of gives you some quantitative feel on a specific data set on which we measured performance. So, starting from a bi-LSTM model, we were able to achieve nearly 20% absolute improvement, going from the bi-LSTM to the final model that we had. And the final model we had also allowed us to better trade off precision and recall compared to the initial Roberta model that we trained. And in terms of production impact, we were able to leverage this model in a human-in-the-loop offline system and accelerated annotation throughput by 5 times from the baseline LSTM model and reduced false rejects by close to 20%, right? And we were also able to scale this to multiple languages and such with minimal architectural changes.
Right. Wow, this is impressive, I think, and very ingenious to use large-scale transformer language models and use it for task which is where you have to look across all the utterances that are coming in at scale. And I think, like, especially for explainable AI, there is this component of human in the loop system. So it's very novel in the ways that you're combining and lending the power that these large scale language models bring to the table, but like using it in the service of these annotators. So very novel and very creative in the way you're addressing this issue. I so at this point, I think we've gotten a sense for how Alexa, what happens behind the curtains when you say that wake word. We were able to see the technical challenges that you have to solve to be able to deploy this at scale, and we did a deep dive in a specific error pattern recognition and improvement sort of virtuous loop that you have for NLUs. As an Alexa customer, I'm particularly excited to know all this, but I'm also excited about like what's around the corner. And I think you've done some work in natural turn taking, so would love to know a little bit more about work that's being done there and what we might get to see in the near future.
Yeah, absolutely. So, as we keep saying in Amazon, it is still day one. And one of the things we are looking at, right, I talked about error correction and error detection and how we are improving the core components. But we are also constantly working to enable natural interactions with your Alexa devices, right? One of the things we have been looking at is what is called as natural turn taking. So to sort of give a overview of what we are trying to do here, the ability for you to just say the word Alexa and have a device respond to you is pretty magical. If you think about it, 10 years ago, a system like that was still in science fiction, right? And today we almost take it for granted. But look at our own human conversations, right? How are our conversations? We are not repeatedly spelling each other's name when we are talking, right? Sometimes I'm talking to you, sometimes I'm talking to a third person who might be in the room. We talk over each other, and sometimes we interject when two people are talking because we have something useful to add and such, right? So this is sort of what is called as the natural turn-taking problem. And what we have been looking at is how we can combine cues, both audio and linguistic cues, as well as even visual cues in terms of whether you're looking at the device or looking at the other person to decide when is the right time for Alexa to respond, right? And so we have been, we announced our work on this last year. Here is a illustrative video of this upcoming feature, right? I'm not sure if you can see it.
I can see the video. Yeah, the audio though is not coming through. Let
Are
me,
you able to hear the audio play?
not the audio, but I can see the video play.
Okay. Maybe I can quickly just talk to this video
Yeah.
then,
Hmm.
which is that, here you have a couple of folks who are standing together and interacting with a Alexa device, right?
Right.
Um, and sometimes they are talking to the device, and sometimes they are talking to each other. And all of this is happening free flowing, right? They're not
Hmm.
continuously saying Alexa this, Alexa that, and such.
Right.
So they are, here, for example, this lady is looking at the device and looking at what is being shown on the screen.
Hmm.
This is a common experience that you might have, right? If you're ordering pizza or looking for a pizza recipe, you will get a list of them displayed,
Right.
and Alexa reads it one at a time. Um, and uh, so they make a selection. They can just look at it and say that one, right? As it is reading through, and Alexa will be able to figure out which particular entry in the list that you selected based on that.
Hmm.
And so on and so forth, right? In each of these cases, right?
Right.
Again, you look at it here, the two folks here are talking, but not to
Hmm.
Alexa, right?
Mm.
And now they're both engaged with Alexa.
Right.
So you can see this is a pretty complicated problem from a AI point of view,
Yeah.
although it is quite uh, natural in regular conversation,
Mm. Right. And
right?
I think there's an added challenge of, I think there's a notion of directed versus non-directed speech. So as you mentioned,
Mhm.
the two people on the screen here, they're talking to each other, but Alexa has to sort of know that it's not directed towards it. So just monitor the conversation, but not necessarily interject. So there are a
Mhm.
bunch of very interesting challenges here. And I think this fusion of two different modalities, and doing that at scale, I think that must present like a ton of challenges, and a lot of
Mhm.
interesting technical problems to solve here. But given the track record, it definitely feels like the Alexa team is well equipped to take it to the next level. Pretty excited about what's around the corner with natural turn taking.
Yeah. So with our last year's announcement, we also put out a blog post
Mhm.
that folks interested in can go and look at. Um, so that's sort of a quick overview of things I have been working on.
Right.
Um, yeah.
Thank you so much, Pradeep. I think this was a fun conversation. It was a
Mhm.
really nice journey, starting from how Alexa was conceived and how it was grounded to all the stuff that needs to be done to make it viable
Mhm.
across devices at scale, in different languages, providing
Mhm.
services to developers. It's been a fascinating journey. One of those breakout successes in tech. So thanks for coming here and sharing this journey with us, and super excited for what's ahead
Mhm.
from the team. We all here at Fiddler have like a lot of respect for the Alexa team. So very excited about what's coming out next from Alexa.
Absolutely. And thank you for the opportunity and, great conference.
Yeah,
So look forward to the other talks as well.
thank you. And
Thank you, guys.
before you guys jump off, our next session is going to be on data-centric AI, development for trustworthy AI by Alex Ratner, who is the CEO of Snorkel. Thanks everyone for joining us. Take care.
All right. See you guys.